Hello, everyone. Um, Nice to see you. It's really fun to be back in DevOps. Just seems like just a few years ago we were here and launched Amazon Corretto. So this feels like home. Thanks for coming. My name is Yishai. I'm the manager for programming languages at Amazon. And today I want to talk about my thoughts about Rust and Java. This is not a Rust versus Java talk. If you want to learn about the Rust language, you should have gone to Alex's talk earlier today. I will not be teaching Rust or showing it. I'm going to do some interesting comparisons. And it surprised me. So I hope it's going to be fun and entertaining. It's going to surprise you as well. So I'm Yishai. I used to work on .NET until 6 years ago. Started the Java team at Amazon. And a few weeks ago, we joined the Rust team, where we build the Rust language and a bunch of Rust core features with the Amazon Corretto team in one organization. And part of that, I wanted to learn a little bit more about Rust. I did some basic exercises, hello worlds, but I wanted to know more. So we decided to do this talk. And before we go there, what do we do at the team? Both teams, both the Corretto team and the Rust team, are very active in their respective open source projects. We're developing new ideas, we're building, we're contributing. Obviously, each project has different governance and different contributors. We spend also a lot of time on supporting. So the unique thing about us is we both build the languages, but also have a lot of internal customers using them and looking for, what do I do now when I build the software, but what happens in a year, what happens in 2 years, what happens in some cases in 10 years for the software we build? How do we keep maintaining it, upgrading it, securing it, making sure it runs without bugs and it doesn't crash and there's no operational issues. And the biggest thing at Amazon is we keep growing and growing and growing, and we want to keep our costs in the same place. So optimization and performance are also pretty important for us. So I want to share with you what I was thinking about Java and Rust. I'm much more familiar with Java. Like people at Amazon that know me will say, hey, he's the Java guy. So for me, this is how do I learn about Rust and how do I get started? So let's take a step back, and it's quite interesting when we prepare this. So Java was invented mid 1990s, now about 27 years, by James, who I think was talking just now in another room, as a way to deploy applications for embedded systems and network devices. And we're obviously in a very different place today, right? We're building web applications and desktop applications with it. Rust was invented about 10 years later by Graydon to create a better way to develop system software. Both of them were trying to take C++ and make something better out of it. I know these are very, very vague words, but the idea was we had this language of C++, it was popular, and we try to make it safer, we try to make it easier to code in. And both of these languages don't actually live in the place where they were conceived, right? Rust is now expanding into both the Linux kernel, but also into building web applications. You see a lot of companies now taking their big apps that they wrote in Java or in Go or in Node, and now moving them to Rust to get better performance. So made me curious, and I wanted to see what it actually looks like. So what do people think here about Rust? Do people think Rust is easier to code in than Java? If you think that, please raise your hand. Yeah, I think we kind of agree. Do you think that a Rust application will perform better, run faster than Java? Yeah, everybody? Most everybody? Half the people? That's what I thought too. We thought in going into this exercise that Java will have a much larger set of ready, robust frameworks. It's obviously been around for a lot longer. It'll be a lot easier to build an application. We thought that Rust will outperform Java. We thought that Rust will start up a lot faster than Java, and in some ways that's true if you look at Hotspot, but we have Ground native today. And what I wanted to do is come into this test not as a benchmark, not as let's take these, you can see a lot of Rust and Java benchmarks in the wild. Let's take an actual application that was not built for Java, not built for Rust. Let's start from scratch and port it, or port the idea of this application to Rust, port it to Java. Let's see what happens. When I talk about Java in this talk, and if you've seen some of the previous talks, I'm trying to explain that Java is just a lot more than the Java programming language. But for the purposes of this discussion, we're sticking to Java, the programming languages, not Kotlin, not Scala. We're going to run it on one or two JVMs, Hotspot or GraalVM native. I also mean the rich core libraries coming with Java. So whatever comes in the JDK, for the purpose of this discussion, I consider Java. There's a lot of interesting other things to look at, which is if you want to compare languages, you might say, I don't like Java, but I like Kotlin. I really like Scala or Clojure or whatever else. Or there's also this case of there's a lot of applications running on Java. So when we think about Java and we invest in Java, we don't just invest in, I can program faster in Java or better. I also want Kafka to run better on Java. I want Spark to run better on Java. But for the purpose of this discussion, we're just going to take two applications and put them side by side and see what happens. So a quick, very, very shallow dive into the big differences between the two languages. So with Java, we have the virtual machine. We basically abstract away the operating system. We add a garbage collector. We manage thread pools for the user. We have an object-oriented methodology, so it means you can take a class and derive it, and now you have a vtable that at runtime, the invoker is going to go and pick which virtual method you're going to run. We have reflection, things, you could do things dynamically. You can change the code dynamically, at least for now. You can observe things that you didn't even think about could happen at the beginning. You can add agents. There's all kinds of these dynamic alterations at runtime you can do. In Java, we mostly allocate on the heap. So when you new an object, it's going to go to the heap. When we look at async programming, or I want to call it high concurrency programming, we have Project Loom coming in to make it very easy for us. When it comes to how we compile the language, we have either Hotspot, where we have a 3-layer system. We're going to interpret the code, and as it runs more and more, we're going to compile it with C1 and then C2. Or we can go with a Graal approach, where it's pre-compiled. In contrast to that, Graal tends to be a lot more like a C++ compiler, basically. You have safe and unsafe modes. You have the language is monomorphic, which means you don't take and derive objects. You can apply traits to objects. We allocate on the stack by default, which tends to be a pretty nice performance gain when you can do that. And we only do AOT. There is no dynamic compilation in Rust. It also means we compile everything from source every single time. Nobody takes libraries and jars and dynamically loads them. We take all our dependencies come in on source code, we drop them in on disk and compile them all at the same time. The thing that attracts my attention the most is memory. We always think about, can we improve the CPU utilization? Can we run a little more efficient code? But almost always when you look at apps that have been optimized, a lot of the remaining issues are how much you allocate, how much memory do you use, how expensive is that memory, and how expensive it is to allocate and deallocate it. And these things tend to be hidden in C++ applications, mostly hidden in Java because the GC is doing the work until the GC starts working hard and your latency starts climbing, and you got to go start fighting it and chasing it. And when we look inside Amazon, about half our consultation has to do with which flags should you use for G1, and the answer is take them off. take all these flags out. It got a lot better in Java 17, and you mostly don't need to tune it, but people still tend to do it. We have the JIT, which is pretty nice. It can sometimes do escape analysis. It can take objects off the heap and put them right in the register, or maybe even sometimes, in some cases, in the local stack. And the other thing we have in Java is every object, once you allocate it, it has a header. The header is another 128 bits. It adds support for locking. It adds support for hash codes. It adds support, there's a pointer to the class object. But most objects in Java are pretty small. With our data, we think, from our experiments, about 60% of the objects in Java are less than 2 words. So the overhead of that header is quite significant. Where in Rust, you allocate on the stack, objects are just what they are, just the data that you put in. So the memory consumption tends to be smaller. Since heap allocation is opt-in, you have to go and box the object so it goes on the heap. The pattern is kind of like Java in terms of allocating. You bump a pointer in the stack, or you move the stack pointer. The object is there. Your code exits. The stack gets bumped. Very cheap, very almost free. In Java, the allocation is free, but the deallocation could be more expensive. So I think I covered this area. We have trade-offs in the JVM. We're allocating over objects really quickly. You don't see much of that as the program goes, but as you start cleaning them up, it starts to cost you. We still have memory leaks in Java, and they happen because you have static objects or static maps that hold onto objects. You forget about them, and you're back to square one when that happens. Fortunately, not a whole lot. And memory management is a hell of a lot easier. If you ever developed in C++ and went to Java and then came back a few years later, it's icky, right? It's like, oh my God, I have to really think about the life of every object and clean it up. And it's really nice. Once you fall into Java, it's great. But again, when you look at an app, we talked about it a year later, 5 years later, the load has grown. And all of a sudden, the app that was responding in 10 milliseconds now responds in half a second sometimes. Especially at the high latency, at the tail, your P99 request might be a lot higher than you expected, and then you start having to work really hard to get that out of the way. We talked about compilation, and in Hotspot, the compilation contributes to startup time. We have a lot of projects in Java to go and fix it and improve it. One of them is Graal Native. We have Crack. And Creo projects are trying to freeze the JVM and get it started quickly, so this starts working better. And why do we care? We care in a cloud when we want to auto-scale. We run 10 machines, now we need 2 more. We need these 2 machines to come up very quickly. We want to add a new container to Kubernetes cluster. We don't want to worry about warming it up, and we want it to be added as soon as possible to take load. So it is still a trade-off today. Especially if you're using open source software, there isn't a great solution yet to start up a Java process quickly enough in many of these types of applications. In Rust, when you want to allocate in the heap and you want to start sharing objects, it gets tricky. You get reference counting. The algorithm is not as easy to use. It's not as trivial to keep up with. We encourage you to use ownership. We encourage you to borrow and lend objects. Whoever went to Alex's talk, you can see how confusing it could be and how much time it takes for you to mind shift from coding in Java to coding in Rust. So the old patterns just don't work, and you just got to get used to the new system if you want to accept it. So with that, I know it was very kind of basic, shallow. These are the 2 systems. What did we want to do? We took an app, and we took 2 developers. One of them is one of the Rust compiler developers. One of them is one of the Shenandoah developers on the JDK team. And we said, you guys go pick an app, and let's take something that's relatively small, go port it, go build it. Let's see how it went. How fast did it take you to build it? what obstacles you run into, and what was the performance at the end. And again, what tools did we use? What libraries did we use? What preconceptions the developers had along the way? We also flipped them in the middle, so the Java developer did some Rust work, and the Rust developer did some Java work. And so let's talk about Magic Wormhole. That's a Python application used to copy files across the network in a, you can call it, safe way. What we have is we have the registry. The registry is an HTTP service. You give it a name, it gives you back an IP address, and then a sender takes a file, uses that IP address to push the file into the receiver. In our case, we implemented just a one file transfer. There's no concurrency. It's kind of an easy startup test. Want to see how it went. So both setups implemented the receiver, the registry, and the sender. And initially we said, I mean, they have a day job too. They don't have to prepare my presentations. We said, you got 2 days. Do whatever you can in 2 days. Let's see where it goes. When people get excited about stuff, they don't stop after 2 days. It ended up being a lot more interesting and a lot longer. And honestly, it was pretty cool. I learned a lot from just observing the behaviors of the people on the project. And ideally, we wanted to limit the code to less than 300 lines for the whole thing. One of the developers did it. The other one got excited and added a bunch more features into the service. So we ended up with a little under 300 lines in the Rust version, about 800 lines in the Java version. We did expect Java to be a little more verbose, but it was longer, not because Java was verbose, because we just added a lot more features. We had feature creep. We have all the great examples of projects defining themselves as they go. So if we look at the Rust implementation, what we see here is we see Hyper. Hyper is an HTTP client. It is developed one of the Hyper developers is on the team. So we go and talk to the registry. We get the username and the port. We then bind to a TCP listener. And then we go and take this, the header that comes in from the sender. We split it, we get which file we want to put in and where we want to put it in, and then we just basically start writing these bits. You can see it here. The Tokyo IO copy copies the content, awaits it, and writes it into the file system. And what you see here is concurrent programming in Rust. Tokyo is our async, one of the async frameworks, the one we're working on in Rust. If you want to look at what is the core of the program, where most of the time is spent, where the cost is, it's these lines of code. We read something for the stream. We await it. So we let the thread go to rest, and we copy the content into the file. We await again, and that is it. And then what did we use? So what did we go? What did we use to build this application? So obviously the Rust compiler, but beyond that we use Tokyo. Tokyo is the async framework. Clap is the command line argument parser, and Warp, which is the web server that was used for the HTTP communication. And then we use Cargo. Anybody familiar with Cargo here? Okay, about 30%. So Cargo, you can think about Cargo as Maven. We have Cargo and crates. Cargo would be the package manager, and the crate would be the package. Crates.io is Maven Central. What surprised me here is we have Cargo Flame Graphs, which is a profiler that's built into the package manager instead of into a standalone tool. But this happens. Other languages do the same thing. .NET has .NET tools, and Cargo seems to follow the same pattern. And then, so we got one person going and building the Rust version. And then we built the Java version. What you see here, somebody tricked me. So this is what I saw for the first time, but it turned out it was a second or third iteration. But what we see is we take basically an IO and we use channel transfer 2 and copy the file extremely efficiently. And if you ask me where the rest of the code is, I'll give you at the end the GitHub repos, and you can see all the iterations, all the commits, and everything that happened in the process of building this. So in Java, we used Micronaut, Jackson, and Netty, although some of these got removed along the way to get more performance. Obviously Maven as our package manager. And then for runtimes, as you notice, conspicuously missing from the Rust, because Rust doesn't really have a runtime like Java does. It has a very thin one over C library with a very, very few implementations there. We use Hotspot 18, and we use GraalVM 22, which is equivalent to Java 17, and it's the community edition. Let's start talking about performance. Let's start talking about how this went. So we took a physical server just to make sure we have exactly the same machine every time. There's no differences. It's a i7 machine. It had a spinning Rust hard drive, which you can see this as the gun in the first act, and it's going to come back in the second act and the third act to bite us. And then because we knew this is basically a CLI, right? And as soon as I saw this, I looked at developers. I'm like, you're not serious, right? We're going to take Java, which is known to be slow to start up, and we mostly use it to build web applications, and we're going to do a CLI comparison. Totally unfair for Java. Why would we do that to ourselves? So given the time that we have, we decided to continue with it, but we said, let's just transfer really big files, and that's going to amortize the startup time in the process. And then we're at this point, and we want to do another iteration on this and explore it further. We're giving the Java and the Rust sender and receiver, we're going to ask them to handle a single file at a time and not multiple files in parallel. All the files come from disk, so we have basically an IO-bound application here. Theoretically, we could have put the files in memory and could have done multiple files, and we would have been here spending, I don't know, 2 weeks, 3 weeks to get it all right and done, and we wanted to just show you a sample and just feel these two frameworks or two languages. So this is the first result that I got. And if we're looking at this, on the left side, you're going to see the wall clock time. We immediately start diving further and looked at kernel time and user time. And I'd say let's ignore the right side. Let's just focus on the left side. So as you notice, there are more implementations here than 2. It's already 6 implementations. And it's a good thing, right? The developers started building something, didn't really like the results. Let's try something else. Let's see how it goes. And what we see is on the left, we see Graal. Then we added, so this was Graal, if I believe correctly, might have even had Micronaut on it. Then we took that out and added NIO to Graal. We had Hotspot, and then we did Hotspot with NIO, and then we had Rust. And Rust took about 10 seconds to transfer a 4 GB file, and the others took about between 4 and 2.5 seconds. Anybody finding this surprising? That's not what I expected to see at all, right? Any ideas? Anybody have thought what's going on here?
Await things in Rust. You're awaiting 2 separate things as opposed to just streaming them over the bus.
Okay, so Rust await. It's a good theory. It actually is close.
The kernel primitive are not the same, so it's not using the same API in the kernel, so it's less efficient.
Yeah, that's true too. So in this case, what it ended up being is this implementation used Tokyo, the async framework, but it explicitly used Tokyo file system. And Tokyo file system implementation favors stability under high load. So you don't get into a mode where the threads are being starved because you don't have enough I/O. So it ends up being slower by default. And that was a great discussion then with the Tokyo implementer, and like, why are we doing it this way? And the answer is, this is explicit. This is what we wanted to do. But when IOU ring becomes available in much more operating Linux distributions, we will implement IOU ring here, and Tokyo file system will also be a lot more efficient. When is it going to happen? I don't know. We have to discuss it. We have to look at it. There's a lot of things that have to happen for this to take place. But this was surprising. I did totally not expect that. And then we looked at memory. And memory was, I don't know, much more expected, although, again, pretty stark comparison, right? Hotspot takes 160 megabytes, Graal takes 80 to 60, and Rust took just 5 megabytes. So that was pretty neat, and that is what we see most of the time when we use a Java application versus a Rust application. Of course, this isn't quite real. And anybody can guess why. Why is that not a fair comparison?
Because you have the whole JVM in Java.
Right. But, I mean, you do have the whole JVM. So,
Sure.
right. So,
Rust application will scale more linearly.
no. This is a single file. So we have a single file transfer. You have a CLI, reads the file, reads a buffer, copies it over, reads the next buffer, copies it over, shuts down when it's done. So the reason here is when Hotspot comes up, it loads the compiler, it compiles the app in memory, it spends a bunch of CPU on it. There's a lot of classes being loaded that might be necessary, might not be necessary. This is the minimal footprint that you can get out of Hotspot. In Graal, we don't have the compiler. You still have the footprint of the classes being loaded. So it's a lot smaller, but it's still not very, very small. And in Rust, we just have the minimal amount of classes that we need or code that we need and the buffers that we allocated. So what we should see here, if we start doing high concurrency, things are going to start equalizing. If you're going to have 1,000 concurrent threads or concurrent tasks trying to copy files, things are going to look a little bit better in favor of Java. We haven't quite built it, but these are the things that we see. Still, Java will still be less efficient because of the heap allocations, because we have a GC that just keeps chasing the app, and we need to give it spare memory because of these extra headers that we talked about earlier. So overall, we think this is a reasonable comparison, but not always you're going to see these stark differences between Rust and Java.
Graal, that's a version. It's ahead of time compilation.
Yes, correct. Sorry, that wasn't clear here. So if we try to summarize it, what we found, this all happened, the first part happened in a day or two. We found it was pretty easy to write in both applications. The Java developer actually, day-to-day is a C++ developer, so he said it took him a very long time to learn because he had to learn Micronaut along the way and learn about NIO, which he didn't know about. So in 2 days, he managed to learn a framework, learn new APIs, build an app that worked pretty well. That was pretty impressive. And the same with Rust. It was pretty easy to go figure it out and build something that worked okay. Obviously, the Hotspot JVM was slow to start. As we warmed it up, as we know with Java, it gets the throughput that we needed. We were surprised by the file system performance. It was very interesting that somebody working on Rust day to day was not aware of these limitations. I think a lot of it has to do with these frameworks are new. There's not a whole lot of experience with them. There's not a million Stack Overflow posts on them and blog posts, and we keep learning and improving them. Rust better at memory utilization, and obviously Java has a lot more mature libraries. There are a couple of other interesting things that I saw along the way. So the Java developer didn't really like using dependencies, right? We teach people in Java, you can do so much with the core libraries that just do it, right? Don't bring in stuff from Maven. You'll hear a lot of talks about don't bring small libraries that you don't need. If you can just do the code in 2 lines, your security will be better, you have less update burden. Java keeps compatibility a lot better than third-party libraries. So he tried really hard to go and work with Rust core libraries, and that's just not a thing, right? If you want to use an HTTP stack, you need an HTTP stack, right? You almost everything you need to do in Rust beyond the most basics, you go and get a library using Cargo. The last thing that I lost some sleep over, let's look at the time. So if you notice, Hotspot took a longer time than Graal, and it made sense. But as we start measuring, we added a timer that just measured the transfer time. And what we noticed was that Java is running a lot faster. Actually, Hotspot runs faster than Graal, but at the end of the app, Hotspot just stays alive and doesn't go down for another second or so. And what we learned is that because we're using spinning Rust, because we only have 64 megabytes, if I go back again, here's our smoking gun. You have 64 megabytes of cache and a old technology hard drive. The operating system is now using the memory to take that and flush it to disk, and that takes time, and Hotspot is going to wait for it. Which also tells you something about memory, right? You think that Rust was a lot more efficient in this case, but really what happens is the operating system is still holding these multiple gigabytes of memory before it can write it to disk. Your app is not as efficient as you think it is. And you want to observe what's happening on the whole operating system and not just your heap memory or even your native memory in Java. There's more effects happening on the system as you write your app. Don't forget about that. That's pretty critical. And we tend to kind of narrow down and just think about the language, right? And the things we build, but they all have interaction. Okay, so this was done. But you know what happened? We had 2 developers, and they both seen each other's code and each other's performance and start getting kind of like, why is Rust working so slow? Or why is Java not doing as well as it did? And they got really excited. And yesterday, 4:45 a.m., I get this message on Slack from one of the developers, and he said, I really don't know how to put all these graphs in Excel because we built the first graph in Excel, but I ran everything again, and I made some changes to both the Rust app and the Java app, and I wrote a Python script to generate some graphs for you, and here's a tarball. Boom. And I'm like, buddy, I'm talking tomorrow. I'm not going to be able to put all your stuff in, right? What are you doing? But I'm a geek too, so let me show you what he sent. Totally nerd sniped me. We actually built 3 more versions of the Rust app, and it turned out when I dug in, the data you saw wasn't right. Java actually started a lot slower than Rust initially, right? But then if you go and dig through the commits, you'll see that he wrote that I want to do the transfer just like Rust so I can be as fast. So it started as Java slow, Rust slow, like here, and then Rust was faster, and then, sorry, Java was faster, then Rust was faster. Let's look at it. But what changes did we make? We got rid of Tokyo file system APIs. We just went straight to blocking to see if there's a difference between, so your theory, right? Is it async and blocking? And then we moved to use the send file API to send the file across the network. In the Java app, we learned that the teardown of the app in Hotspot was slowed by the OS disk synchronization, so we switched to use temp file system, basically to give Hotspot a fair shake. We also started with the HTTP stack instead of a full Micronaut application, instead of using straight TCP. And we dropped it because we're competitive and we want to see that what is the actual difference. So I think somebody here mentioned earlier, you use a different API, you use a different syscall. And at the end of the day, right, both these languages work on top of the operating system. They're not doing a lot of things themselves, or sometimes they do, but in these kind of basic operations, it's all about finding the right syscall underneath and knowing which API to use, much more than the language feature itself. So let's look at memory again. So I'm going to show you these 3 iterations. I'm not going to go deep into the details of each one. I think it's kind of hard to see the numbers, so I'll read it for you. So Graal using HTTP consumed 180 meg and Hotspot about 300, 299. And then Rust with blocking, but with Tokyo file system used 5.6 or 5.6 something. Then we moved on to the second, where we start using NIO, and Graal dropped to 82 meg and Hotspot to 250. And now you can see, because we moved to blocking in Rust, all of a sudden Rust tripled its amount of memory. And it all has to do with just more buffers are being run in memory and big buffers, and yes, the memory grows. And then in the last version, where we dropped a bunch of libraries, extra libraries, Graal dropped to 60 megabytes and Hotspot to 230, and Rust with 2 new implementations were around 14 or 15 meg. So you can still see the big difference between the languages in memory. It's still really stark. And why do we care about that, right? So think about us, we're a cloud company, right? What does it mean being a cloud company? It means we're a data center company, right? We build data centers, we stuff them with computer, we chop them to bits, and then we give you virtual machines, right? And the more memory we stick into the virtual machines, the more expensive it is to build these data centers, and the more we have to charge you when we rent out these machines to you, right? So the more we can do on our applications or on your applications at memory reduction, the less we have to buy the hardware and the less we have to rent it out for you. So we're really interested in reducing memory, both in Java. So that's why we're participating in GC optimizations, because making the GC chase stuff faster. And Kelvin's here? Over there? Yeah, so Kelvin is talking about Generation Shenandoah, which is another way for us to reduce memory in Java. We have Project Lilliput that's going to go and reduce that header size. We care deeply about reducing the memory in Java. But with Rust today, if you can implement an application in Rust, you're going to start off with less memory. As we saw, you're not necessarily going to get better performance, or it's not going to be that stark. But memory is likely going to be a very stark difference. So let's look at time. This is actually the first iteration. That's the one I didn't see at the beginning. So at the beginning, Graal HTTP run 28 seconds, and Hotspot run twice as fast. Because now, if you implement it inefficiently, the startup time doesn't become such a big deal, right? And then Rust async run. These are just different files again with the first implementation. So the numbers are slightly different. They were about 10 seconds, and now we see 9 seconds, 7 seconds. But roughly the same performance we saw at the end. And then we started optimizing. So we added NIO to Hotspot. And what you can see now, this is the 2 bars. The left bar is the actual transfer time that we measure. And the right bar is start of the app to tear down of the app, or start of the process, tear down of the process. And what you can see here on the right side is the difference between 3.5 seconds and 3.3 seconds is mostly Graal startup time, pretty fast, right, about 200 milliseconds. And in Hotspot, you see another 1.7 seconds, which is the startup time. But if you look at the transfer time, Hotspot is still more efficient than Graal native, which actually makes sense, right? We have an optimizing compiler, it's JITting it, it's using profile-guided optimization, and here we have Graal CE that pre-compiled the app. It's not as efficient. We know that some of the performance optimizations are in Graal Enterprise. So again, if you run an app, and these are roughly the numbers we also see in production, if you run an app on GraalCE, you're going to get some degradation in throughput, but you're going to get the benefit of quick startup. And the other thing to keep in mind here, all of this is running on the serial GC, which is the only GC available for Graal native, and we wanted to make Hotspot and Graal native operate under the same conditions. With Rust, we took Tokyo file system, which we now knew has a limitation, and we took it out, and the numbers dropped to about 3.5 seconds. Very comparable to what we get out of Java, not as good. And then I actually don't recall what was the last iteration, but the point is that when you show developers that somebody's doing better than them, and you show them existence proof, they're just going to go and get it, right? And they don't stop. But now, if you notice, we ended up at the same place, right, for both languages in terms of performance. So at the end of the day, what I'm trying to say is, if you pick a language and you think the language is better, you might be surprising yourself. I definitely surprised myself in this. I was expecting Rust to outperform Java. It did not. It doesn't mean that with 2 more iterations, one will actually not beat things even further, and not with, once we start adding features, like we want to add CRC validation, concurrency, it might start skewing again. So don't be afraid to iterate. You build something, you want to pick a language, right? Go build a prototype, right? Try it out. Build in 1 or 2 or 3 frameworks. Everything you think you know tends to be different once you try it and once you iterate on it. Don't just give up on the results once. I started in Java. We've seen a bunch of cases. I think Volker is here. We just seen a case a few months ago where somebody built something in Java. It was very slow. He built in Rust. It was very fast. Conclusion, Rust is much faster in Java. And then you double click on the app and you used completely different algorithm, and what was slow was the algorithm choice in Java versus the algorithm choice in Rust, and nothing to do with the languages. So just don't be afraid to iterate. Measure, 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 measure. Measure, look at counters, profile the app. In Java, we have a lot of metrics, right? We had JFR and JMX and HSPerf, and there's so many ways to look at the app. Look at it. Don't just build it and ship it and call it done. The thing in Rust, we talk about that, is picking the dependencies. You can't just use the core libraries. If you come from Java and you're used to the JDK being so awesome with so many features, the situation with Rust is different. It's separated, it's intentional, it encourages competition between components, it encourages a lot more, it's easier to keep compatibility in the core language. It's just different. I think we covered already the idea of GC and object headers and startup memory. But for Java, the thing again, most of the things that I'm experiencing in Java is you can still in Java reduce your allocation rate. And when you reduce your allocation rate, your results, your latency, your performance are going to be a hell of a lot better. We have a lot of great tools in Java to do it. We have JFR, we have heap profiling. You can just grab a heap dump. You can look at what's in your heap. Take a look. Take your app, dump it, look what's inside. You'll be surprised how many stuff is there that you just don't need. And you'll just get a lot more performance out of Java without having to go to a new language. Like I mentioned, the experiment here is not complete. This is the first talk that we're doing on this subject. We're going to do another one in a few weeks in San Francisco. We want to come back in JFocus and next year in DevOps with a more deeper, fuller comparison. It's great, by the way, to build apps. You might have these core engineers working on something else, working on your infrastructure, core frameworks, common libraries. If you are them, or if you're their manager or you're their peer, make them build an app for real. They're going to learn a lot of things along the way, right? We learn a lot of things along the way, and we're going to make these core libraries better for everybody else. And the last thing is, performance is a really shiny object, right? If you dangle performance in front of developers, they're just going to start following. If you're a manager, just know when to take it away because they're not going to stop. Um, and I talked a lot about prototyping. I can't say it enough. Prototype your ideas. Writing a document, doing a presentation is all fine and dandy. If you build a prototype that behaves like the app, you're going to learn a whole lot more. And you're going to end up with a much better A, app, B, convincing yourself it's the right app, convincing your leadership or whoever funding it. Prototype, hack, do it again. It's such a powerful tool. It's going to propel your career. It's going to propel your company. And it's not expensive. It's much, much cheaper than sitting in 20 meetings with your program manager or product manager or your manager. So what's next? We have all the code on these repos. So Esteban wrote the Rustic wormhole. So you can go into his code. That's the Rust code. William, who was very excited, forked Rustic wormhole and made improvements. You can see the code there. And then William wrote the magic wormhole in Java. That's the last one. If you're interested, go in there, look at the commits, see how it went, see kind of the inspiration from one to the other as the process proceeded over time. It's pretty cool. And give us feedback. If you're interested in Rust or interested in Java and we think we completely botched it and we did it wrong and there's a much better way to do it, this is not an application we actually use anywhere. It's a toy, but very interesting toy that we just want to keep evolving and talking about and showing. Maybe do a few more of these. You're more than welcome to come in, comment, copy, do your own talk, throw us pull requests, bugs, whatever you want. And then we'll see you again, maybe next year, maybe JFocus, with the next iteration of the story. And that is it. And if anybody has any questions, I'm more than happy to answer.